Sir, you are muted.
Thank you. Okay, so I was just sorry. I was giving a long spiel, but so I should repeat. I said that last class we introduced this useful notion of what's called a group action on a set, and we saw it appearing in various contexts. Permutation group sort of tautologically acting on a set, then GLN acting on a vector space, or subgroups of GLN acting on a vector space. Then in an exercise you saw that Z mod 2Z acts on the complex numbers by complex conjugation. Okay, so there are various situations where there are groups and there are sets on which the groups act. Groups acting on subgroups, a group acting on its subgroups, okay, a subgroup acting on the group. Okay, so also, okay, so and why do we study? I mean, if there is, why do we try to abstract out this notion? Well, the hope would be that there will be some formula or some theorem that one can prove in this generality that we can apply in all contexts of group action without having to prove it each time anew. Okay, so that's the reason why we abstract out this notion. Okay, and so that okay, so in order to that we need to make a few more definitions. Okay, one we saw last time called the orbit of an element. Okay, so it is the elements. So given an element little x in the set X, it is all the x prime to which a group element will take x2. Okay, so we can sort of pictorially think of it as an orbit. So that's the under the action of the group. That's all the places where x will go and come back. I mean, okay, this is not some circle, but at least in our mind we can think of it. That's why it's called an orbit. Okay, so if for all G, so I'm just going to recall the definition. Okay, there exist functions. There exists a function phi g from x to x, okay, such that satisfying two conditions. Phi 1 is the identity map on x, and for all g1, g2 inside G, phi, the function corresponding to the product is the composite. Okay, so this is what we have. And then we also talked about orbit. Just hold for a minute. Orbit of X is the set of all points to which X is taken to by this action. Okay, so this is what we did last time, and we looked at various examples. Okay, so now I want to just change of notation. Often it would be clear from the context what phi g is for each g. Okay. So in that case, instead of writing phi g of x, we will abbreviate it as gx. Okay. Just we can pretend that we are doing some scalar multiplication. Okay, but just sometimes it can make it right. I mean, because after a while, we never write some phi gx, we just write gx. So so at least this gives me an escape clause that I already. Okay, so I think it is just easier. Okay, if you're confused, just write phi gx. But if you're clear what the thing is, just write gx. Okay, so it's just, I wasn't, last time I said I will not introduce this notation, but today's lecture, when I was preparing, I realized that if I didn't introduce this notation, or everything that most of the things that I write will be very cumbersome, okay, and tedious and difficult to read. It's okay, not difficult to read, but doesn't carry any information. It's once we understand that this is what we mean by gx, then it's okay. You just write like this. Okay, so today, so today we want to define a new thing, stabilizer of x. Okay, is the set G in G such that Gx is equal to x. That is, on x, the function phi g acts as identity. Okay, so let me just for now let me clarify what this means. That is, phi g takes x to itself. That's what it means. Okay. So yeah. Okay, so so the first observation that we want to make about stabilizer is, for all x in x, the stabilizer of x is a subgroup of G. Proof. So let x be inside x and write H for the stabilizer of x. Okay. So then, so 1 belongs to H, since phi 1 of x is x. Phi 1 is the identity map, so it is true, in particular for little x. Okay. Now let G1, G2 belong to H. This implies that G1, G2 of x. So this is just an abbreviation again. Let me just remind you. This is just, we said that we take, again, this is just phi g1 of phi g2 of x. Just for the first few minutes, I'm just elaborating what the notation means. Okay, and this is g2 belongs to H, so this is g1 x, which is x. G2x is x, then G1x is x. So we get this. So G1, G2 is inside H. Okay. Now let us take G1 inverse x. Okay. So how do we compute this? So notice that G1, so what is G1 inverse x? So G1 takes x to x. Yeah, so okay, so what is this? So let me just for now, let me okay, but 5G1 inverse x. Okay, just for now, let me just elaborate this one. This is what, I mean, we saw that phi of G inverse is the inverse function of phi of G. So, and phi g1 is a bijective function. Okay, it takes x to x, so its inverse will also take x to x. Okay, it's bijective. Okay, so note that. Bijective, and phi g1 x is x. Okay, so phi g1 inverse of x is also x. Okay, so this is a subset of G. So hence, H is a subgroup of G. This is okay. Yeah, it's a subset which contains the identity closed under the group operation and contains inverses. Yeah. Okay. So let's go back to our examples and see. So this is our from last class. Okay. One, Sn acting on the set 1. So we know that the orbit of any element is the whole set itself. Okay. So let's call this thing X. For all I inside X, the orbit of I is X. That is because given any I and any J, there is a permutation which sends I to J. So, so therefore, orbit of I is X. What about the stabilizer? So let us look at the stabilizer for N, just because notationally it is a little easier. Okay. So stabilizer of N. This is the set of all permutations sigma in Sn, such that sigma of N is N. That's the definition. So again, it is in these places that it is convenient to write sigma of N as opposed to phi sigma of N. So maybe I'll just do it once more. Okay, last time. I mean, unless. Okay. So stabilizer, but what are the permutations in Sn which would send N to N, but no other? This is the same thing as Sn minus 1. That is, okay, for permutations of 1 to up to N minus 1. So this is the to consider this. Okay. Now let us look at some other I. Okay. So let I be X. Yeah, let's just take two elements, I and J be. So we would like, okay, so write H sub I and H sub J for the stabilizers respectively. H sub I for I and H sub J for J. Okay. So let us look at the relation. Then, so there is an element of Sn. So let sigma be the cycle transposition Ij in Sn. Okay. So I'm doing this specifically for S, which we will prove in a few minutes. But it is a concrete situation. So, okay. So now, okay. Hi is sigma Hj sigma inverse. Okay. So that is Hi and Hj are conjugates of each other. In Sn. Yeah. Okay. So this is what we would like to show. So let us prove these in both directions. So in the specific example, we will use that sigma squares identity, but that's not really relevant in the proof. So we'll prove, okay? But let us still try to prove this concretely. Okay? So we would like to show both inclusions. Which one should I go? Okay, so I will do this first. So let H1 be inside Hj. So that is H1 of J is J. Then sigma H1, sigma inverse, this group element acting on I. Okay, so sigma takes I to J and J to I. Therefore, sigma inverse will take J to I to J and J to I. In other words, sigma square is identity. Okay. So this is sigma H1 of sigma inverse I. Okay. This is just by definition of a group action. So this is sigma H1. Okay. Sigma inverse of I is J. Okay. So that is sigma sends I to J and J to I. Therefore, sigma inverse also does the same thing. And in fact, sigma square identity. So sigma is sigma inverse. Okay, so I mean, just to clarify. Okay. But H1 fixes J. So this is just sigma J. But sigma J is I. So the conclusion is that sigma H1, sigma inverse is inside H. So now let us prove the other direction. I mean, the general proof is also not very different from this. It is just, now it is concrete. We can write down some numbers and check that this is, I mean, we can follow the proof. That's. So now we would like to take an element inside Hi, prove that there is an element in Hj. So let H2 be inside Hi. Okay. So we want to show that there exists H3 inside Hj such that H2 is sigma, Hi is sigma, Hj sigma inverse. So if you take any element in Hi, it can be written as sigma times something in Hj times sigma inverse. Okay, so this is what we want to show. Well, there is an actual candidate. I mean, if this has to hold, so we're going to work backwards. Just for an aside, maybe I should put it in a different color. Maybe I put it in green. Okay. So if or working backwards through the proof, if this has to hold, okay, there is only one choice for H3. Which is that sigma, so we multiply by sigma inverse on the left side. Okay, so we get sigma inverse H2, then the sigma inverse and sigma cancel, then H3, and then we multiply sigma on the right side, get H3. Okay, so this should tell us what we should define H3 as. Okay, so let H3 be sigma inverse. So this, whatever I wrote in green is, it is just, we are thinking through the proof to see what we should, what element we should look for. Okay? Sigma. Okay. It's enough to show now that H3 is inside, this H3. Hj. Okay. So let us check that thing. Okay. Sigma inverse H2, sigma of J is sigma inverse H2 of sigma J, and sigma J is I. This is sigma inverse of H2I, but H2I is I, and sigma inverse of I is J. That's what we checked. Therefore, sigma inverse H2 sigma. So maybe we should say, we should write this later. So it's enough to check this. So we know if what we're trying to prove is true, then it must be this element. Okay? So we just check if that element will work. So this is inside Hj. So let H3 be sigma inverse H2 sigma, and this finishes. We wanted to find an element H3 satisfying this condition. So this finishes the proof. Proves both containments and proves that these are. So this is a property that we will prove in more generally later. But right now, I just want, it's easier to just do this concretely on this Sn action of S. Okay. Next example that we had was that H subgroup acts on G by translation. Okay, so phi H of G is Hg. This is for all H. H for all G is H. So yeah, so it's a little. The reason why I use the elaborate symbol phi H of G is that if I just wrote Hg, then it would sound like there's some tautology. It is not. I am defining phi Hg to be Hg. Okay. So then, okay. So let us look at. So let us look at the stabilizer. So let G be inside G, and H be in the, and H an element of the stabilizer of G. So that would say that phi H of G is G. Okay. But what is this? That is Hg is G, but then now cancel with G on both sides. Multiply by G inverse on the right side. This will give Hc. And we already saw that it is a subgroup. So therefore, stabilizer of G is the singleton, the smallest possible subgroup, which contains the sliders. Okay. So third was this GLN acting on, or third or fourth or something was, okay, GLN acting on Rn, GLNR acting on Rn. Okay, so this I will outline in an exercise, because you'll worry about a little bit of linear algebra, etc. while we look at this. Okay, so outline in an exercise. This. Okay. So yeah, so this the few. In this context, there's a few. They may be known to you, but you may not have thought. Few facts in linear algebra which may be known to you already. You may have done prove something, but you may not have taught in this language, this sort of setup. So I would like to just this example, I would like to postpone so that I can develop it sequentially. Next is for G acting on the set of subgroups. Okay. So let H by conjugation. Okay. So that is okay. So what is the action? Phi G of some subgroup H is its G conjugate for all G inside G and subgroups H of G. Okay. So now, when would we have? What would be the? So of course, what is the orbit? It's all the conjugate subgroups. I mean, sort of by definition. What is the stabilizer? So let H be a subgroup. Okay. Let G belong to its stabilizer. Okay. So then GH, G inverse is H. And that means that GH is equal to HG. So maybe I should clarify. What do these things mean? I think we discussed this once. Okay, so this is the set of all GH, G inverse such that H is inside H. This is the set of all GH such that H is inside. G is fixed. It's a fixed element of its stabilizer. This little h is the only thing that is actually going to be quantified over there. And this is HG such that H is inside H. So in other words, the left coset of G, left coset GH is also the right coset HG. Of course, this is not saying H is normal. Okay. Because for that to happen, this should happen for every G. So, warning. This is only for the given G. And it does not imply that H is normal. Okay. For which it is necessary that this happens for every G in G. In other words, every G, okay, for that, it is necessary and sufficient okay, that for H to be normal, GH is equal to HG for all G inside G, or equivalently, the stabilizer of H is G. So this is just one should keep this in mind. Okay. Whatever I wrote here is for that specific. But yeah, okay. Okay. So I will. So now we will try to prove some useful results about orbits and stabilizers and the relation proposition. I am following Artin, but I forget which chapter this is from. But I am not doing everything in each chapter or each section. Okay, so I will do these basics. So there's an extremely interesting stuff about these finite subgroups and symmetries of objects, which can be discussed at this stage, but it would take the rest of the semester, and we will not get to. We will not. I mean, I would like to prove zero theorem, and at least, After that, if we have time, we can revisit this question about symmetries and rotational and symmetries of three-dimensional objects. Two-dimensional we will do after we prove the zero theorem. That you should see. But whether we can do it in for solid objects, I think we will not have the time. Yeah, but yeah, but it's actually, I mean, that's also developed in the same chapter as this in Arden's book, and it's very interesting. Okay. So this generalizes the observation that we made about symmetry. So G acts on a set X that let me not repeat it all the time. Let X be inside X and X prime be in the orbit of X, be an element of the orbit of X. Then the two stabilizers are conjugates of each other. And the stabilizers of X and X prime are conjugates of each other. This is what we had seen in that specific example. Okay. I and J are two elements in X. Okay. That there is a permutation which takes I to J. So I and J are in the same orbit, okay. And their stabilizers are conjugates of each other. Okay. That's what we see. Right. Hx and Hx prime for the stabilizers of X and X prime respectively. Okay. So there exists G, G in G be X prime is G. Okay. Such a thing exists because they are the same orbit. So claim, so analogous to what we had claimed earlier. So let me write it, let me get it in the right direction. H prime, X prime is G X H G. Okay. So that's what we would like to prove. Okay. And this is, so it is the G which takes X to X prime that gives the conjugation. So proof of claim. Okay. Let us prove that the left side contains the right side. Okay. So let us take an element inside HX. Okay. So let H be inside HX. That is HX is X. Then GH G inverse applied to X prime is GH applied to G inverse of X prime. This is bracket. That's a prime. Okay. Which is, so G inverse of X prime, G takes X to X, G takes X to X prime, G inverse will take X prime to X. These are bijective functions and inverses of each other. Okay. GH of X, which is G of HX, and that is G of X, which is X prime. So GH, G inverse is inside HX prime. So this proves this continuity. Okay. So now we will not reprove the other direction. Okay. We will just apply, allude to symmetry in this thing of the argument. So, okay, so if G takes X to X prime, okay, then okay, G HX, G inverse is inside HX prime. So now G inverse takes X prime to X. Okay. So by the same argument, okay, G inverse Hx prime, G inverse is inside Hx. Okay. Same argument. I mean, same argument applied to G prime, taking X prime. I mean, G inverse. Okay, so applied to X prime being taken to X by G inverse. Okay. So here, what we used was that X goes to, I mean, G takes X to X prime. So we just use, I mean, G is some arbitrary element, right? So we could apply the same argument to this also. I mean, G is not an arbitrary element. G takes X to X prime, but G is an element of G. So we can apply the same thing here. Okay, and so this would imply that Hx prime is inside. So multiply on the left by G and right by G inverse. And this proves that. Okay, so stabilizers of two elements in an orbit are conjugates of each other. So this is a useful thing. Okay, so now I want to introduce a new action which we have not discussed so far. Okay. Okay. So let H be a subgroup of G, then G acts on the set of cosets G mod H. Okay. This is just a subgroup, not necessarily a normal subgroup. So we're not discussing a. I mean, G mod H need not be a group. It is just a set. It is a set of cosets of H. Okay. By. So again, just for elaboration, I will write phi G. So this is the function phi G. A coset will look like, say, AH. This is GAH. I mean, the coset, so that is G takes the coset AH to the coset GAH. So phi G, this is what. So this is a useful action, and let us. So we would need to study this. I mean, at some point we would need to look at the action of G on the set. Oh yeah, okay. So proposition. Let us look at this. For the above action, of G on G mod H1. Sorry, I need a definition. Sorry, before this. Maybe let us look at this thing before we make the definition. Okay. In the above action, if AH and BH are two cosets, then there exists a G such that phi G of AH is equal to BH. Okay. That is, for example, take G to be BA inverse. Okay. This is an element of the group. There may be other choices, okay, but this definitely will work. So, in other words, if every element, for every pair of elements, x and x prime in that set, okay, they are the same orbit. So, in other words, okay, this action has only one orbit. That is, for all x and x prime inside x, okay, x prime is in the orbit of. That's what I mean. This is what we have. Definition. Okay, as definition. Let's G act on X. An action of a group G on a set X is called transitive. Okay. If the above thing happens, if for all x and x prime inside X, there exists a G such that Gx is equal to x prime. Or equivalently, there is exactly one orbit. So another example is the action of Sn on the set 1 through n that we discussed earlier. Is a transitive action. Okay. The action of G on subgroups is not transitive because a subgroup can only go to its conjugates, and conjugates have the same cardinality. So a subgroup of say size 5 cannot go to a subgroup of size 6. So it is not transitive. I mean, there are other ways also you can express this. Okay. Okay. The action of GLN R on Rn is not transitive. Okay. Okay. That is for all V inside Rn, but not 0. There does not exist G inside GLN R such that GV is 0. So a non-zero vector cannot go to the 0 vector. So this is not a transitive action. So there are various ways of. Okay. So there are many actions that we see are not transitive, but action of G on coset space of some H is transitive, and permutation groups is always sort of by definition. I mean, we worked through the. I mean, if you worked through the exercise last week, you said that essentially permutation group acting on 1 through n is exactly what a permutation group does. So that's not. It's all a tautological state. Okay. So here are some transitive actions, some non-transitive actions. So with this, we can probably state the proposition. Of course, the first part of the proposition we already proved. Let H be a subgroup of G1. The action of G on G mod H is transitive. And 2, the stabilizer of H, the coset H, one times H is H itself. I mean, this is the coset, okay, but that's the subgroup. Okay. Proof 1 already done while motivating the definition of transitive action. And 2, okay, suppose that, so let G be in the stabilizer of the coset one time H. Then okay, so then phi G of 1 times H is just GH. But on the right side, okay, so G belongs to GH since 1 belongs to H. Therefore, G belongs to H because these are equal. That's where the stabilizer is. I mean, G belongs to GH for any group element, but because that GH is equal to H, G belongs to H. Okay. Conversely, for all H inside H, phi H of 1 times H is H times H is H. And this is, there are, I mean, two. We're proving that 2 sets are equal, and we prove the 2 inclusions. So this is an action of G. Okay. So now we come to one of the key results about this group actions. Here, orbit. Maybe I should make one more remark. Okay. Let G act on X, and say A inside G let be an orbit of that. Single orbit. Okay. I'm not saying A equals, sorry, A inside X. Okay. So that is, A is the set G X G inside G for some X inside A. It is an orbit of this action. Then G acts on A, I mean, restricting the action of transitive. Okay, so proof of this is left as an exercise. You should do it to make sure that you understood the definitions. Okay. It is, I mean, it is not at all. I mean, essentially, it follows from definition, and therefore you should do it to convince yourself that you understood the definitions. Okay. So now we are ready to state. Time is 11. Okay. Now we are ready to state this important result about this. It's called orbit stabilizer theorem. Okay. Let G act on a set, and G is a group. Okay. Let x be inside x. Let h inside G be the stabilizer of x, and A inside x the orbit of x. Then there exists a bijective function let's call it epsilon. I don't know why they calls it epsilon, so I don't want to think through carefully. So A sending some GH to GX. This is the stable orbit of X. So GH will go to that. That's what we would like to do. Okay. Moreover, okay. So now we have two sets. Sorry, just give me a minute. Moreover, this action, so I will, this function commutes. I will explain what this means in a minute. Let me write it. The action. G mod H and so let me clarify what the final sentence means, and then we will prove the first.
Sir. Sir, are you here?